First of all, studying the global electric circuit requires experts across many areas. Scientists who specialize in the uppermost atmosphere, solar wind, electromagnetism, chemistry, the physics of lightning, cloud formation, volcanic weather, and more. Secondly, the model is trying to encompass events that are a part of the global electric circuit on vastly different time and spatial scales.
This is the world's strongest magnet, capable of sucking objects in, generating electric current.
Can you see that?
Yep. And levitating non-magnetic objects. It even wreaks havoc on camera equipment.
Wire's magnetic, so if it's a CMOS sensor,
the electrons just can't find their way.
well, they get redirected.
So yeah, if you notice bad video or audio, know that it's incredibly hard to shoot in these magnetic fields. A portion of this video was sponsored by Google. I came to the National High Magnetic Field Laboratory in Tallahassee, Florida, where since the year 2000, they have held the Guinness World Record for the strongest continuous magnetic field.
Somebody left a chair where it wasn't supposed to be. It then got accelerated across the cell, completely pulled the guts out of the chair. Now we all have those nice, super uncomfortable wooden chairs.
For reference, the magnetic field of the Earth is 0.00005 Tesla. A fridge magnet is around 0.01 Tesla. MRI machines can get up to 3 Tesla. But this electromagnet creates a magnetic field of 45 Tesla, so nearly 1,000,000 times Earth's magnetic field. To achieve this field, the magnet consists of an outer superconducting magnet and an inner resistive magnet.
Can I put my finger in the bore? Is that a bad idea?
No, it's fine. You can totally do that.
Let's see. Oh. So that's where there's 45 Tesla.
Further down, a meter away from
a
that.
meter down. And so that just drops down for
It's clear all the way through to the bottom.
Oh, wow.
The maximum field is basically a centimeter tall.
Yeah.
Here we have very small samples. Think something like a chip in a computer or a cell phone. That's what users will come in with. So that's plenty big for what we want to do with material science or condensed matter research.
ramping up this magnet to full power takes around an hour and a half. That's because they have to put 47,000 amps of current into the outer superconducting electromagnet.
47,000 amps.
47,000 amps, 500 volts.
It is so insane.
All right, so let's take it all the way up to full field.
One thing that happens in a strong magnetic field, obviously, is that magnetic materials are attracted to it. We cut open a Nerf football and put in a couple steel washers, being careful to tape it up so the washers can't get out. We also covered the opening to the magnet so the ball won't get sucked down into it.
I got an unmodified Nerf football.
And sure enough, it's easy to tell which ball contains the washers. But making high-field magnets with ordinary resistive wire is really hard.
For a wire-wound magnet like a junkyard magnet, traditional electromagnet, the highest magnetic field you can get is about 2 Tesla. And the reason is that you cannot get the heat out of the innermost windings. So back in the 1950s, Francis Bitter up at MIT, he realized that physics doesn't care what shape the conductor is. You can take your round wire and smash it into a very thin plate. If you then stack those plates with alternating insulators, you make a helix that electrically looks just like that. But now I can push cooling water axially through the stack of conductor. So that means that innermost part, I can now pull all that heat away, which means I can go to much higher currents through these coils, up to 57,000 amps, than what you can do with a traditional wire-wound electromagnet.
The Mag Lab uses a significant fraction of Tallahassee's electricity.
So we can consume with all 4 power supplies at full blast about 8% of their total generating capacity.
What's the electricity budget of this place?
So nominal $250,000 to $300,000 a month.
Holy, yeah, that's a lot.
So we operate in their federally mandated reserve, which every utility has to have. They have to have that available to push into the grid if there's a problem. We have a deal set up with the city so that they can actually make money off that power that they have to produce, but which they can't sell. The flip side is when they need it, we ramp down, and we can go down much faster than they can spin up a Jenny.
Why do you need 45 Teslas?
There are a couple things that drive material discovery. One of them is just growing a new material. The other one is putting it in an extreme environment, like high magnetic field, high electric field, high pressure, ultra low temperature. Another axis is taking an existing material and improving its cleanliness. So getting all the impurities out. So as you drop the impurities in the material, you're reducing where the electrons scatter from in there. And that improves the properties, enables you to see things that you were never able to see before. We've only just barely scratched the surface on what can be done with this. People are going to look back about 25 years from now, and this will be the inflection point, this 5-year period.
The shrinking quarter is one of the most popular attractions at the Mag Lab's annual open house. And no wonder.
Combines all the good things of a science project. Light, flash, certain sense of danger, noise, excitement, and yet proves a very important law of basic physics and does something which could not be done in any other way. And it uses a magnetic field.
This cool experiment shrinks a U.S. quarter
The Mystery of High-Energy Cosmic Rays. Presented by Science at NASA. Hold out your hand for 10 seconds. A dozen electrons and muons just zipped unfelt through your palm. The ghostly particles are what scientists call secondary cosmic rays, subatomic debris from collisions between molecules high in Earth's atmosphere.
Scientists have long understood what happens in the clouds when lightning bolts appear, but have never been able to precisely explain how lightning is created until now. A new study published Monday in the Journal of Geophysical Research appears to have solved this mystery using math. It details the powerful chain reaction that occurs in the atmosphere to spark the creation of a lightning bolt. Victor Pascoe is joining us now. He's the professor in the Department of Electrical Engineering at Penn State University, and he led this study. Victor, thank you for being here. How exactly did you and your team figure this out?
Yeah, thank you for this opportunity. We discovered this, we believe for the first time, this powerful chain reaction which leads to lightning initiation. It combines cosmic rays, so we believe that cosmic rays initiate this reaction, and also involves very high energy photons and electrons. And what is really fascinating about this mechanism which we published is that initiation occurs on a very short time scale. So if you think it takes only 1/1,000,000th of a second for lightning to initiate. And the way it works like a domino effect. So you can think about high energy domino when you really just touch it, and then it develops in a very powerful electron avalanche leading to lightning.
So tell me then, how should all of us Earthlings be interpreting this study? What should this mean to us?
Yeah, so I think that this study really provides additional insight on physics and situation in our everyday environment on Earth's planet. And we believe that we are able to uncover some really interesting phenomenology related to lightning. For example, Professor Nikolai Ostgaard and his team recently conducted research using a high-altitude NASA ER-2 airplane to get very close to lightning discharge. And what they discovered is that lightning appears to be producing, this lightning initiation region produces a lot of gamma rays and X-rays. But these regions at the same time appear to be optically dark and also radio silent. So all of us know that lightning usually associated with optical flash and radio noise. So our modeling actually allows to explain these peculiar features of lightning. So also, while we worked on this research, a lot of interesting ideas appeared which are going beyond lightning research.
Like what?
So this photoelectric effect, which we studied, we believe can be applicable also in relatively small volumes, and may lead to some new interesting ideas in plasma science and engineering in research which is in fields which are different from lightning. For example, we're thinking that in small volumes, this powerful domino effect can lead to X-ray emissions, and potentially we can produce new X-ray sources in the future.
Well, it's amazing that it takes 1/1,000,000th of a second, and so much research goes into it. Professor Pascoe, thank you so much for your time today.
There are 3 stages in the life cycle of thunderstorms. During the developing stage, a rising column of air, known as an updraft, pushes a cumulus cloud up into a tall, towering cumulus. This may produce the occasional flash of lightning, but very little rain. Next is the mature stage, when precipitation begins to fall, creating a downdraft of air. When the downdraft spreads out along the ground, it forms a gust front. The mature stage can bring heavy rain, hail, frequent lightning, strong winds, and even tornadoes. Finally, it's the dissipating stage, when the updraft is overcome by the downdraft and the gust front cuts off the warm, moist air that was feeding the storm. Rainfall will decrease, but lightning remains a danger.